Hello, everyone, and welcome back to this third week of our lecture series in engineering the cardiovascular system. We're continuing on from the last session, which we focused on stents for aneurysms, and also we looked at grafts. Now we're going to look at heart valves specifically in this lecture, and we're going to try and go to some rather detailed lengths in terms of describing the engineering solutions for human heart valves. So here we're going to start looking at this interesting video. This is actually one type of human heart valves that we'll be looking at in a minute. It's called the ball and cage. And what you see here is you have two heart valves replaced in this patient. As you can see, there's a rather severe and abrupt motion every time that the heart is beating, and so this actually uh, turns to be quite a noisy valve in reality because of all the mechanical motion and impact involved here. But what's interesting is that still after many years, these have been around for now decades. We still have these versions also used. And nowadays we have two main types of heart valves, as we'll see in a minute. They're either biological or mechanical. And mechanical is actually when the components are, purely synthetic and engineered. There's nothing biological about it. The material is engineering material such as metals and polymers, and they've just been coated probably with another coating that can make it more hemocompatible, blood compatible. And then there's the biological valves, which are basically uh, composed of mechanical parts, but also some component that is derived from biological tissue. Okay, so these are the two main categories. And it's interesting how you can see the coronary flow behind the valves here in the heart. These images are really interesting. And again, you see those um, uh, back there in the image, you see those knots there that belong to as I mentioned last time, the cage in your chest when they've actually cut that center bone and then they've put it back together. You'll see those traces in many of these OCT images. Okay, but now let's move on to today's lecture. So, when we're talking about engineering a heart valve, we should understand under what conditions we see it suitable to replace a heart valve. We should also understand what can go wrong with a heart valve replacement and how long it can stay. Because very much like the stents, these biomedical devices also need replacement. So if they're not functioning properly, we have to replace them. Okay. So, as you remember, mainly heart valve disease refers to the case where uh, the natural and healthy functioning heart valve, which you can see up there on the right top side of this slide, is a very healthy heart valve. When it actually isn't able to fully close in these cycles or fully open, meaning that it's not doing its valve behavior properly, it's actually considered an unhealthy or diseased heart valve, like the graphic that you can see underneath that. In these cases, even when the valve is closed, you get some leakage flow, and when it's actually trying to open, you don't see full opening. So there's blockage of the blood going back to wherever it's going. And so that actually doesn't allow that fresh blood to come in the next cycle. And there's always going to be mixing. And as I mentioned, the fluidic variations, the vorticity that blood has to have for the pumping to be efficient is all going to be influenced. Now here, you're looking at the two types that I mentioned, an example of each. So in one example, you can see a mechanical heart valve here, and here you can see a biological heart valve replacement. And here you can see the surgical procedure, which is used to introduce the valve to the patient's heart in an open surgery setup. All the sutures have been made that basically you see the threads running already through that outer lining and ready for it to then be pushed onto its proper location and installed. You want to do that ahead of time if you're the surgeon, because you don't want to do that while the heart is open. Okay, so everything is prepared, ready, and for this to go in, and then you've got these the proper material here. Sometimes it's silk, sometimes it's degradable, but basically the two types of valves have their own pros and cons. If you ask a surgeon, they're going to tell you if you want a lifelong durability, well, lifelong we mean 20 to 25 years, not really lifelong. You want to go with mechanical. They tend to stay there in a good operable condition for longer. The problem with them is because of the material not being super hemocompatible, they actually require anticoagulants to avoid. So basically, you inject that in the patient's bloodstream to thin the blood and to avoid clots and thrombosis. So really, you have to account for that non-biological aspect by making the body of the patient more tolerant of this condition. That's why you add anticoagulants to avoid coagulation of blood. And the problem with that, of course, in all patients that use anticoagulants is that they have bleeding complications, meaning that if they bleed, blood clotting won't happen as efficiently, so they will have an issue overcoming that bleeding condition, and the bleeding will just go on because the clotting and the platelet coagulation there won't happen. So it has its own pros and cons. If you're a youngster, God forbid, hopefully you never have this issue, but they will probably suggest the mechanical one because you don't have issues as much and your body can still manage. If you're a little bit older, the elderly are always recommended to use the biological ones because anticoagulants can be very detrimental to their health. And so there's usually a tendency, depending on your age, depending on your other disease conditions and stuff. And then when it comes to the biological or bioprosthetic ones, they do not require anticoagulants typically, but what happens is through time they degenerate. And as much as they try to coat these surfaces with, glutaraldehyde and other agents to kill the cells and avoid the immune response, they gradually get degraded through time. And I'll talk about their composition, but basically they have the same composition of human tissue, animal tissue, and so calcification can happen. All the stuff that happens to a natural heart valve can happen, but here it's more severe because it's actually from another body to your body. So it's an external body, and as much as it can get remodeled, but it's usually more often than not is going to get degraded and needs a change within 10 to 15 years. So each have their own pros and cons. The choice is yours and, of course, of the surgeon. Another issue with the mechanical ones is they're a little bit noisy. Every time the heart beats, they make a noticeable sound, which you can hear as a patient. And that's not really very pleasant. But anyway, this is the process to, again, administer and install the heart valve replacement. And it's the most it's known that the most common heart valve replacement is for the aortic valve, whereas the mitral valve is the most common to be repaired. So they usually try and replace it. They instead attempt to repair it. And the other two, the tricuspid and the pulmonic valve, are rarely replaced, okay, or repaired in either of those cases, right? These are the least common. First of all, they don't have those issues as much because they don't see that much pressure and that much initiator of detrimental effects that could damage it. Therefore, the damage is less. But also, the functionality level, even if there is an issue there, it doesn't change as much as to influence the patient's health significantly. So, unless there's a really big issue, those don't usually get changed. And here, what you can see is that ball and cage valve that I told you about. It's a very clever mechanism for back, decades ago. The ball goes back and forth, blocking and opening the way. They've got the tilting disc, very nicely designed. It goes through that metallic rail line there, basically, as it rotates back and forth. They've got the bi-leaflet, which looks very much like a car AC vent. And in the biological ones, you see all sorts of variations. The St. Jude's one, they've got their own design. It's a tri-leaflet, very interesting way they've actually put the tissue basement there. This is, again, it's a piece of tissue from either a pig or a cow, very rarely from a human, but it sometimes is if you have other diseases that don't allow you to use cow or pig tissue. But basically, this is from the heart. It's from the heart tissue of a cow, that surface lining. Usually they do some denaturation, so basically they denature the proteins there. They do decellularization, so they get rid of the cells. This is all left as a protein backbone with all the stuff, and then they use it here. This is Medtronic's design. They have their own interesting design here. You've got Edwards here, and then you've got the Soaring Group. Just a few examples, really. There are lots of more examples out there, but these are just a few to show you all the variations that you can see in terms of the design. Back to mechanical valves, as I mentioned, you have more than 200, 250,000 valves replaced every year. And these actually used to last, much less than 20, 25 years. They used to just last for 3 years. And thanks to all the coating technologies to make these more and more hemocompatible and eliminate hemolysis and, issues associated with blood clotting, they're now even more durable. But hemolysis wasn't the only issue. The backflow that you got from the design, some of these designed, especially in the case, the ball and the single leaflet here that you can see there, the Medtronic Hall, or what we call the spinning disc. These had the issue where you could have recirculation of the flow behind the barrier, and their failure to go back to their original state. Okay, so the design wasn't perfect. And the other issue with the ball was, as you know from last lecture, it's like a barrier in the flow. And what happens is that it actually has all the drag forces on it. So it changes the flow regime to a more turbulent blood flow, even when it's not supposed to be turbulent, right? And so the damage occurred by that as the blood rushes through the next sector of its vascular circuitry, can be detrimental. And as I mentioned, the noise from these mechanical valves is also an issue. Usually the metallic pieces, either in the ball and cage or the spinning disc, or the other ones that use metals, are cobalt, chrome, or titanium, our favorite. Very inert and biofriendly, as I mentioned in the last lecture. The moving part is metal, but it's coated with something that we call DLC, diamond-like carbon. And that's the main reason we use that, or pyrolytic carbon, is to actually reduce the amount of wear and elongate the lifetime, basically, and the durability of the valve. The ring around it is a material you've already heard of, EPTFE. You remember Gore-Tex from the previous lectures, and it's usually this fabric on top of a metal rim. Main problems with this is really thrombogenesis. So they initiate thrombosis, and that's why we use anticoagulants, because the material actually isn't that non-adherent to blood cells. So it actually starts accumulating blood cells and coagulation. And endocarditis, sorry, it's not inflection, it's infection here, is the infection of the internal layer of the heart, or it can be the infections that grow on the surface of the valves. And that also is, more pronounced in these mechanical valves as it grows quite fast, because it really doesn't have any means of fighting that. The material there is purely mechanical and passive. And then we have the biological valves. And as I mentioned, the good thing about these is that, they actually don't need anticoagulants. They're able to behave like normal tissue in the heart. They have very high collagen content. That's why, they're extracted from the pericardium of these animals. And they are usually, again, placed on a sturdy mechanical fixture, such as a metal or polymeric skeleton, as you saw in the images, or you can see here actually. So they're installed on that. They're very nicely sutured to it. So you can see this sort of, it's the sewing here, you can see it around there. And basically, this sewing ring around is what holds it all together. It's a very detailed and fine process to produce these also. We might talk about it a little bit in the next lecture. And then they use glutaraldehyde, which is permanently cross-linked to the surface to actually get rid of the cells and basically avoid the immunological response that can happen and initiate thrombosis and clotting. So we actually eliminate that by using, glutaraldehyde. And basically, they're usually produced by basically extracting the material in the tissue lining of an animal's heart, or sometimes they're extracted from, again, the pericardium. And then in some cases, it's actually the exact valve in an animal's heart, which we extract, like usually from porcine valves, and then we actually do denaturing, and then we do decellularization, and we get rid of all of the native tissues. Sometimes now we're moving towards a time where we culture the human cells from that patient. They could be pluripotent cells, which we've switched to the cell line of interest, and basically induce that differentiation to the proper muscle cells or epithelial cells or endothelial cells, and then we've coated these valves with those in order to become more friendly to the tissue, and so it doesn't get rejected. But in the old days, and still the majority of it is just, we don't put any cells there, it's just denatured from the animal. Finally, we have to look at the issues and complications that can happen with heart valves, as well as the success rates. So as you can see in these graphs, and I mentioned before, the life expectancy for these valves really is different. The bioprosthesis or the biological valves tend to, degrade a little bit differently from the mechanical ones. They reach that, need for replacement a little bit sooner, but in general, they both need to be replaced if you're talking about longer periods than 20, 25 years. And what you see here is that in terms of the diseases that can happen, the issues that cause the valve to be non-functional, it's usually the same suspect. So it's thrombosis, where you have the buildup of um, platelets and blood cells in the form of a clot and the form of a plaque that sticks to the surface of these um, valves and the vessels around them. Thrombo uh, emboli. So this is when you have an embolism, detachment of that same thrombosis lesion, the clot, basically the cluster, and that can actually move on to then attach to one of these surfaces or stick in a cornering junction in these mechanical devices. And then the other issues are associated with the anticoagulants, which you have to use, which again, they cause their own issues. Okay, so there's a variety of things. So endocarditis and hemorrhage. So valve endocarditis again is the case where you have the infection of the valve surface. And so each of these can have their own complications and therefore um, require another exchange of the valve for the next 10, 20 years of that patient's life. In terms of the valve itself, these issues are more biological, which can happen because of the natural reaction of the tissue and the biological system surrounding the valve. But really, in terms of the heart valve itself, you can have fracture, you can have fatigue, just like any other mechanical component. But one that's really highlighted here is cavitation, because sometimes the blood pressure drop actually, vapor evaporation basically happens either under increased temperatures or reduced pressures, meaning that you reach the vapor pressure. So sometimes the reduced pressure in these circulation systems causes evaporation, and the bubbles that form then cause cavitation on these surfaces. And just like the cavitation that you see in, submarine, it's no different from that. Operating under, these conditions, you see the IPV rating for your cell phone and other electronics, and they tell you, you can have it under X meters of water, let's say 10, sometimes 100 meters. But then for a known period, if you leave it there for 10 years, it's not going to be safe anymore. Maybe for an hour, right? Maybe for a couple of minutes, okay? So operating under the blood flow, the pressure, the fatigue cycling, because you constantly cycle from high to low, high to low. These really make it hard for these materials to survive. That's why metals are really good. Plastics have issues. And so, all sorts of issues can happen, but cavitation is a big one there. The valves, especially the tricuspid ones and the biological ones, can tear apart from calcification and the biological issues that we mentioned. They can also tear and get damaged mechanically. So basically, we're really looking at either 10 to 15 years if it's biological, or about 20, 25 years if it's something that's mechanical. So in terms of these two plots are really showing the need for replacement for both of those valve types. And you can see there's pretty much, you see that need for replacement. The majority of people happening around, somewhere between 10 to 15. And this has changed quite a bit, but it really is pretty much the same. And through time, we've really improved on the material and design aspects. It used to be only, as I mentioned, 3 to 5 years. Now it's 10 to 15, and even for the mechanical ones, you see even around 20 to 25 years. So this really concludes our discussion on the valve selection, different types of valves, heart valves. But please note that the design of a heart valve goes way beyond these that we've looked at. These are just the basic features, really. If you look at the design of a heart valve, although we've covered the majority of what is here, but you have various components, right? You see here that the way this is wrapped around, the way that it's sewed onto this material here, okay, and the installation, the manufacturing of it, right? Tiny changes in the shape of these curvatures here and these surfaces can actually result in major changes in the performance and the longevity of these devices. So all of this is really both studied experimentally and also computationally, and then finally in vivo in the body for companies like Edmunds and Edwards and St. Jude's Medical or Medtronic to actually arrive at an optimal solution. It has taken many years, and it's a big sector, but still, there's lots of room for research, lots of room for us to learn more and more about these valves and their performance optimization. So I'll leave it there for this session. Hope you've learned some good chunks of information here, but we'll get back together for the next session soon. Take care.